Dear students, today we will see the new topic, that is a Miller index based some numerical problem. In the last lecture we have seen corresponding theory also. So what is the Miller indices actually? Miller indices is used to specify in specific direction and plane. Okay, for in the crystal, with the Miller indices I can specify for the particular direction or plane. So generally this direction or planes could be in the lattice or in the crystal. If you take any crystal, you know the basic things are you have a complete periodicity, you have a long range order, and all are you have a number of unit cell, you know everything. We are not going in depth in that. We are seeing the numericals now. Actually this is a mathematical notation. This is a mathematical notation to represent plane or direction in crystal. That's it. Here I have come with some numericals that will clear your doubts. Okay, first problem here is, what is the angle between 110 direction and plane 110? Always please understand the direction is normal to the plane. Okay, here the x and y and z are the axis. So you can take this also x and this also y, or this is z, any direction. Here we are taking this is x and this is y and this is z. That's it, no more. Okay, first we will see for this direction 110. So when you see, this is a origin. This is a origin. Okay, this is a origin. If this is moving, if this is moving along there is a vector, right? The vector is moving, that is a move to pass through the origin of the unit cell. You can see now. So this is pass through the origin of the unit cell. This is origin, please understand. If you put for 110, you want it, there is a coordinates is x coordinate 1, y coordinate 1 and z coordinate 0. That means no coordinate for the z point. So the projection will be 1 on 1. So the direction will be like this. So this is 1 by 2. There is a 0.5 a. So that means I am considering the distance, unit distance of a. Okay. So this is 1 means this will be 0.5. Okay, so 1 1. Okay, so with the direction it is, don't think about this plane. Okay, first think about this only the direction. The like you can see that is the x1 y z it not touching, z you don't have any direction, the vector have only in the direction of x and y. So when you see the plane will be x and y, z not touching, just parallel, you can see, not touching the z plane. So it touching only the x and y plane. Okay, just parallel to the plane, z axis. Now, so let me, that is a problem. The following planes are given here. So diagram is given. We want to find the plane as well as the direction for the given plane. Okay, so the notation, you know, 3 notation I will remember. If you put for direction, it should be in the square bracket. If you putting for plane, it should be in the round bracket. Similarly, if you are putting for minus number, if you represent the minus axis, that is it represent by bar. You have other notation also that we will see in the problem. These are the main thing you want to have in your mind. Another thing, the procedure is, first you want to find the intercept, then you want to do the invert the intercept, then you want to find the LCM for the intercept, then you want to multiply the LCM value with that intercept, then that is a HKL. H means 1 by x intercept, y means k means 1 by y intercept, and L means 1 by z intercept. Okay, then that value for plane should be represented by round bracket, for direction it should be represented by square bracket. That's it, very simple. So for this given plane, this is a plane, those intercept are with the distance of a, so that means 2a 1A and ZA. The ZA is 2A. So you want to say only the coefficient, you should not say here. The intercept are 2, 1, 2. So procedure is you want to take the invert. So 1 by 2, 1 and 1 by 2. Then third thing, I want to take a LCM for this value. If you take 2, so 2 multiply with the 1 by 2, 1, 2 multiply with the 1, 2, 2 to multiply with 1 by 2, 1. That's it. So if you want to represent the plane, it should be represented by the round bracket. If you want to represent the direction that is normal to the plane, it should be represented in the square bracket. That's it. So now come to this problem. In this problem, the x is not touching actually. It is just parallel to the x-axis. This x is z. The x is here infinity point. X is a infinity. Y it touching at the intercept of a and z touching at the intercept of z. So then you want to invert the intercept. If you do invert the intercept, that is 0, 1, 1. So 1 by 0 is infinity. Sorry, 1 by 0, 1 by infinity is a 0. 1 by 1, 1. 1 by 1, 1. Okay, multiply by 1. So if you take LCM, you will be getting 1. So you want to multiply, you will be getting 0, 1, 1. For plane and direction, it was represented. That's it. Third problem. In this given problem, the intercepts are 1 by 2 in x direction, in y direction it is 3 and z direction at 2. So take a invert. So 1 by 2 invert is 2, 3 invert is 1 by 3 and 2 invert is 1 by 2. Then take a LCM for this. You will be getting a 6. So 6 should be multiplied with this intercept, that is invert the intercept values. 6 into 2, 12. 6 by 3, 2 and 6 by 2, 3. That's it. For plane, 12, 2, 3 in the round bracket. For direction, 12, 2, 3 in the square bracket. That's it. For fourth problem, the intercept at the x is 1. For y is at the minus position. So minus a. It is minus 1a, the coefficient. So for z, a at the 1. So if you invert the intercept, 1 minus 1, 1. So if you take LCM, that will be 1. So just multiply. So represent in plane and represent in the direction. That's it. So if you represent for this plane, 0, 1, 0. So 0 means not touching the x-axis. Y means it touching, exactly touching, you can see. It touching this plane, it touching only y, not touching either x or z. Just parallel to the x and z. It touching just perpendicular, just parallel to the that both x and z direction, just parallel. If you go for 3, 0, 2, this plane at the position of x is 3, at the position of y is 0, at the position of z is 2. So it is inclined, it just inclined to the angle of x and z. And if you see 0, 1, 0 is the direction which is moving in the y direction. This is a vector which you are interested to find. So that we have given drawn for 0, 1, 0. So is x no and z no, not represented, 0, 0. That means infinity. So that is minus 2, 2, minus 2. So if you put a plane for this given value, minus 2 at the x and the y at plus 2 and z at the minus 2. Okay, you can see na x at minus 2, y at 2 and z at minus 2. This is x. It is exactly at minus position. So that is a 2 bar. And y, if you look at, it is at the positive 2a. And z is minus 2, that is 2 bar. Already I said for a minus it should be represented by the bar. That's it. So this is about the direction and plane. Now new problem we will see. This is about we want to find the atomic density and spacing between the nearest neighbor atom in the germanium. So we know that germanium is a diamond crystal lattice. So if you see number of atom in the cubic unit cell for the diamond is 8. How? Because you have 8 corners. You have 8 corners. 1, 2, 3, 4, 5, 6, 7, 8. The 8 corners is shared with the 8 neighbors. Okay, so 8 into 1 by 8 plus 6 faces you have. If you take a cube, you have 6 faces. I hope you understood. In the x direction you have a 2, and y direction you have a 2, and z direction you have a 2. So 2, 4, 6. So 6 on the faces, and each one shared with the nearest near. So nearest nearer means, nearest neighbor means you will be getting 1 by 2 only. Nearest neighbor means you will be getting 2 1. That is 1 by 2. 6 1 by 2. Then the last is 4 at the diagonal. See here one diagonal, and here one diagonal, and here one diagonal, and here one diagonal. So totally 4, right? So here one diagonal, and here from this point, and this point. Similarly from this point and this point. Correct or not? So 1, 2, 3, 4. 4 diagonals you have. Okay, so that will not share with anyone. Okay, that will not share with the either neighbors or anyone. So that means only 4 in the interior. So this is a procedure to find the number of atom in the cubic unit cell for diamond lattice. If you see what is the coordination number, it will be 4. Because see, this is your unit cell. If you take the coordination number, the number of neighbor atom will be 4. So 1, 2, 3, 4. So coordinate number will be 4 for this diamond lattice. Okay, so you know that the volume of cubic unit cell will be A cube. So the lattice constant here, it is given as a 0.564 10 to the power minus 7 written in the centimeter. Here the values given 5.64 Armstrong. This is multiplied with the 10 to the power minus 10, the equivalent value. So it was written by the nanometer. So these are the given, these are already known values for the cube. So these are the basic value for the cube. Already you are familiar in that. So now I want to find atomic density. What is the number of, what is atomic density? Number of atom in the cubic unit cell divided by volume of the cubic unit cell. I am repeating again, number of atom in the cubic unit cell divided by volume of the cubic unit cell. That means 8 what we found, and A cube, so divided by A cube. So what is the A? 0.564 into 10 to the power minus 7 centimeter. Take a cube, so you will be getting 4.46 into 10 to the power 22. Now you want to find what is the nearest neighbor of the atom. You know that nearest neighbor will be 4 only. I said clearly, see, nearest will be 4. For this unit cell, nearest will be 4. That means 1 by 4. Okay, this is a diagram which explained from the top position. See, 1, 2 from the top. If you see 1, 2, 3, 4, that is a corner. So this is a face. This is a face from the top view. Then this is a diagonal. Okay, 2 will be in the 1 by 4th, and 2 atom will be in the 3 by 4th. So that is a representation. So that is the thing is, you want to find what is the spacing with the nearest neighbor atom in the germanium. The formula will be root 3a by 4. Okay, root 3a by 4. So because the diagonal, what is the diagonal for this cube? If you find what is the diagonal of the cube is root 3a. What is the nearest neighbor of atom? 1 by 4. So diagonal divided by multiplied by the nearest neighbor of the atom. So that gives root 3a by 4. That is the nearest neighbor atom. So root 3 into a, that gives 0.244 nanometer. That's it. So now we will go for the next problem. So this is given with the copper crystal. We know that the copper crystal have a FCC structure, that is face center cubic. So first we want to find how many atom are there in the per unit cell. So that means how many atom, if you take a face center cube, so you will be having a 8 at the corners, each will be shared by 1 by 8, and you will be having 6 faces. Only the difference from the diamond lattice is there you have a 4 diagonals, here you don't have a diagonal, that's it, that's easy. So 8 into 1 by 8, that is a sharing, and 6 faces. You know that in faces it would be shared with the neighbor 2 atoms. So 8 into 1 by 8 and 6 into 1 by 2. So you will be getting 4 atoms. Next, if R is the radius of the copper atom, show the lattice parameter A is given as A equal to R into 2 root 2. Okay, so the face is the, generally you know that the face is the square of the side A, and the diagonal will be like a square root of A square plus A square. That is a basic. So you can see here the faces will be, it is shown clearly here. So A and A. Okay, so if we calculate the square root of A square plus A square, we will be getting A root 2. So see, suppose this is a diagram. So if you see the diagonal in this position, 2 R, here R and R, so totally 4 R. Okay, and the diagonal I said here is A root 2. So that means 4R equal to A root 2. Okay, if you cancel, if you find A, you will be getting 4R divided by root 2. If you still manipulate this equation, so you can write like a R into 2 root 2. What is the R? R will be 0.128 nanometer. It is given. The radius is given in the problem, that is 0.128 nanometer. So just multiply, you will be getting 0.3620 nanometer. Okay. The third is you want to calculate what is the atomic packing factor. Each, like either base simple cubic cell or phase cubic cell or diamond, each have some packing factor. Here the formula is, atomic packing factor formula is number of atom in the unit cell into volume of atom divided by volume of the unit cell. So number of atom in the unit cell which we calculated is 4. The volume of the atom is 4 by 3 pi r cube divided by A cube. So the volume of the unit cell is A cube, so that's why I written here. So A, what we have calculated is 2 root 2 R. So we want to take a cube. Then 4 into 4, that is a 4 square divided by 3 pi r cube. Then if you manipulate, if you substitute and cancel the r, and you will be getting like a 4 square pi 3 2 root 2 cube. This 2 root 2 cube. So after that you will be getting 0.74. That is 74% of the atomic factor for this phase cell cubic cell. Then we want to find what is atomic concentration. The atomic concentration can be determined by number of atom in the unit cell divided by volume of the unit cell. The formula is, for finding the mass of the atom will be A divided by NA. A divided by NA. Okay. So here we want to find what is the atomic concentration for the copper, not for any other thing, copper. So number of atom in the unit cell is 4, you know. What is the unit volume of the unit cell? That is A cube. That is 0.3620. So already we have determined 0.360. Okay, that is the volume of the unit cell is 0.3620 into 10 to the power minus 3 centimeter cube. Right. So you will be getting 8.43 into 10 to the power 22. Then we want to find what is the density. that is the mass of the all atom in the unit cell divided by volume of the unit cell. Okay, that is a basic formula. So here the formula will be X into atomic mass divided by Na divided by Na is a Avogadro number divided by A cube. Okay, so Na is nothing but atomic concentration and atomic mass will be 63.55, what you determine. Okay, you can see here the atomic mass will be 63.55. It is given in the problem. You can see the atomic mass of the copper is 63.55. Same I have used. And atomic concentration is 8.43. So 8.43 is substituted. And Avogadro number, so 6.022 into 10 to the power 23. So after calculating, you will be getting 8.9.